Is this bothering you here?
No, it's fine.
Yeah, everything is good, so I think we can start. So welcome everyone. Today we're going to have 3 presentations, as you've seen on the schedule on the website. The first one, Spiro is going to introduce.
Okay, so our first presenter for today is Vatsal, who is a master's student at ITET. He completed his bachelor's in electrical engineering at IIT Roorkee in India, and subsequently worked as an RTL designer at Qualcomm, where he contributed to the memory management unit of the Hexagon MPU. His interests lie in computer architecture and VLSI design. So Vatsal, the stage is yours.
Thank you. So hi, I'm Vatsal, and so this is the first presentation of today's seminar, and I'm going to present on the paper review of a data-driven dynamic execution orchestration architecture called Canon, which tries to bridge the gap between specialized accelerators and reconfigurable architectures. What's happened?
Press the slides once.
Yeah, so this is the executive summary. First, we'll talk about the motivation. So what is our motivation is that there's a gap between the specialized accelerators and the programmable architectures. Specialized accelerators, they are efficient, but they are made for a specific kernel and they fail on irregular kernels. And programmable architectures, they are generic and they run every kernel, but they are quite inefficient. They drive data a lot while computation. So what we propose is a Canon, which is a 2D mesh processing element array with 2 main innovations. First one is the FSM orchestrator, which handles the irregularity in the data by switching its states. And the second one is the time-lapse SIMD execution, which actually amortizes the control. And finally, we conclude with the results that Canon pays a small area and power overhead for its generality compared to the specialized architectures. But unlike specialized architecture, it never collapses on sparse or irregular kernels. This will be the outline for today's topic. So first I'll go through motivation, then give a bigger picture of Canon, then go to the architecture, microarchitecture, and then a deep dive into some of the kernels on which Canon really shines out. And we'll evaluate some of the PPA metrics, go through the strength weaknesses, and then open up the discussion. So our main issue is that modern workloads are quite irregular nowadays. So there is sparsity of 5 to 95% in the activations and waits. There are kernels like sparse matrix multiplication, SDDMM called sample dense matrix multiplication, sliding window attention. And these irregularities are runtime determined. So just a toy example I have added here. You can actually see that if we try to do a general matrix multiplication here, we are just wasting the MAC because we don't want to multiply by zeros, right? So we want something that is data driven. We want to be intelligent here. So this is one of an example of an open source LLM. When you give a prompt to a Mistral 7B open source LLM, it goes through these stages, and you can see that at step 3, step 4, and step 6, you can see there are sparse matrix multiplications happening. So this is quite essential in the modern workflows. And the TPU will actually do a good job here in the step 2, wherever we see general matrix multiplication, but in the sparse cases, it will just collapse. So we have this flexibility and specialization dilemma. So the TPUs and the accelerators, they are quite good at their own work. I mean, the kernel for which they are designed, they have a very excellent performance and wattage ratio, but they collapse on new kernels. And the reconfigurable ones, the CPU, FPGA, CGRAs, they give a broader coverage, but they are having an expensive control, and they lose energy on irregular. They lose energy efficiency on irregular inputs. So what Canon does, it breaks this trade-off by combining static data flow with runtime FSM-driven reconfiguration. So we have the input, and the Canon decides what part is regular, what part is irregular, and we only have to pay the cost for irregular part of the input. And it actually matches the specialized architectures in their own domain, and they retain the flexibility of executing multiple kinds of kernels. So what is Canon? It's a 2D mesh of processing elements, which with static compile time mapping for a regular part of inputs, and runtime FSM-driven orchestration for to handle the irregularity in the inputs. So the first innovation in Canon is the data-driven orchestration. So we have, as we see, we have a 2D mesh of PEs, and each row of the PE is driven by a lightweight programmable FSM, which is called the Orchestrator here. And it actually converts, it takes the input as a metadata and give out the instruction to the PE rows. So each PE row will have one orchestrator. The metadata can be the sparse coordinates of the kernel, the row end tokens, and flush from the neighboring orchestrators and iteration counts. The next innovation here is the time-lapse MD execution. So here we only have one orchestrator throughout the PE array, throughout each row of the PE array, and the instruction runs throughout the same instructions run throughout the row in a time-lapse manner. So it actually helps in reducing the control overhead. So we don't need instruction memory in every of the PE. We don't need to fetch the instructions in every PE, just one orchestrator which controls, which gives instruction to every PE. So this is a higher-level overview of the Canon architecture. As you see, this is a PE array, and as we talked, there are orchestrators on every PE array. We have the instruction-dedicated NOC in the yellow color, so the FSM drives this. Then we have the circuit-switched data NOC. So this is for the feedback from the PE arrays and also to route our data throughout the architecture. And then we have the orchestrator messages to coordinate between various rows of the PE. So here we see when we have a loop kernel, the compiler finds out what is the regular part in the kernel, what is the irregular part, and then it burns it makes the states of FSM and burns it onto the config memory of the FSM. So each PE will have a router to route in various directions, some registers, local data memory, a scratch pad, and it has 4 int8 wide vector lanes for computation. And so each PE has an orchestrator, which is a lightweight FSM. So as you see here, different states characterized to different instruction sets. So if a particular orchestrator is in state S1, it gives a set of instructions called instruction 1 here, and maybe instruction 2, instruction 3, like that. And it keeps on switching depending on the irregularity whenever the irregularity arrives. So this kind of architecture is called an EDDO style memory architecture, because we don't have a single memory, and we distribute the memory throughout the array. So this actually helps in data movement, and it reduces the data movement a lot. We don't need to fetch from a single memory to every PE. So how the compiler flow starts? We have a sparse kernel. So we do the semantic analysis, polyhedral analysis to understand the iteration dependencies. Then we start the data flow design, how we map the iterations on the FSM. And when we are done with it, we generate the bit stream, and we place it on the FSM, on the orchestrator in every row. So now for mapping the A and the B matrices. That is our that was our main goal. So how does the B matrix maps here? So we can take the PE array according to our requirement. Here I've taken a 2 rows and 3 column PE array, and I have divided the B matrix into tiles. So as you can see, the first 1 and 4 comes here, then 2, 5 goes there, 3, 6 goes there, and like that. And so this is the weight matrix that we store in the PE array, and then the input is given. So only the non-zero elements are sent to the PE array through the orchestrator. That part is done by the memory mover or the memory controller, and depending on which row is present here. So k equal to 0, k equal to 1 is present. That means the column 0 and column 1 element, column 1 and column 0 non-zeros will go into the PE row 0, and these 2 column non-zeros will go to the PE row 1. So these are the innovations that we talked about earlier as well. In data-driven orchestration, we have a hybrid scheduling. The compiler programs the FSM for high-level data flows. It can have different states represented by a MAC operation, a send or accumulate or flush operation, and each state has its own instruction sets. And at the runtime, the FSM act as a true data to instruction translator. So whichever state it is present, it will generate that particular instruction set. And in the time-lapse SIMD execution, as you see, each of the PE row goes through the same, each of the column goes through the same set of instructions after 3 cycles delay. So that is a time staggered manner. It helps in reducing the control overhead. We only need a particular orchestrator for one row. We don't need the instruction memory and fetch cycles for every PE. So every PE has 2 kinds of memories. One is the SRAM, the static SRAM, and one is a dual port scratchpad. So this is the EDDO inspired architecture as we talked earlier. And so compiler decides what all stays in the static RAM. As we saw in the example earlier, the B matrix, that is our weights, are stored in the static RAM. And then the scratchpad actually is there to absorb the irregularities, maybe the partial sums of the buffers. So they can be stored in the scratchpad while our PE might be doing some other computation. So just to give a brief overview of where we are till now on Canon. So here's a comparison with what all architectures we know. So with systolic arrays, if we compare Canon, we have added orchestrators, we have distributed the memories, and we have added a reconfigurable network on chip. That's why we are having an area overhead of 30% here. Systolic arrays just compute and data path, so it's quite compact. We have sparse accelerators. That is compared to that in Canon, we have again added the three features as above, but we have removed the decoder and cross parse, which are quite power hungry in sparse accelerators. So still we have an area overhead of 9%. In compared to CG arrays, we have removed the per processing element energy instruction memory. So we are actually saving there, and we are able to get a less area, that is 7% less area. So the Canon eventually recovers area from the CG arrays per PE instruction memory, and it amortizes control via the time-lapse SIMD execution. So let's go to the microarchitecture part now. So this is the pipeline stage of each PE. As we see, there are 3 pipeline stages: load, execute, and commit. So whenever an instruction comes, it is decoded, and then the router actually does the part of fetching the data either from the data memory, the scratchpad, or some of the neighboring PEs, and it gets it into the SIMD registers, and the execution starts. And then we, based upon the address decode of the resultant address, we come to the so we fill the address accordingly in the scratchpad or the data memory or some neighboring PE. Yeah, so this is a basic ISA, which we are using in Canon. It is the opcode, the operand 1 address, operand 2 address, and the resultant address. So here one thing is there that each of these memories, they share a unified space. So that helps in figuring out which particular address goes to which PE. So we don't have to have a conflicting address here. They all the memories, they share a unified address space. And so this is a pipeline execution. So it avoids resource contention as well. And the NOC direction contention, it is avoided by compiler enforcements. So for example, say there is an instruction in load, there's an instruction is commit, instruction in commit, both are trying to get some interaction from the east side probably. So that is not allowed, because that will go to a contention situation. So that is enforced by the compiler here. Now, the FSM has 4 functions. So first is, so it computes state transition condition. So basically, it is statically configured by the compiler. That is the gray part you can see. Those gray parts, they are actually burnt by the compiler on the. They are actually flashed on the config part of the orchestrator. The second is to generate the addresses. As we saw, the opcode, and the operand 1, 2, and the result addresses are generated by the FSM. Then it calculates the next state based upon its current state and the meta data it gets from the neighboring PEs. It calculates the next state and set of instructions for those next state. And it generates the orchestrator messages to notify the upstream or downstream rows that, okay, or maybe I have completed my MAC operation, so I'm flushing the data, please accumulate it, kind of that kind of stuff. So the semantics of states and messages are not hardwired. So the compiler defines them per kernel and prefills the LUT. So talking a bit about the LUT. So it's the same hardware we can use for different bit stream for different kernels. So here in the Canon, we are using a 6 KB lookup table, which actually corresponds to 1024 state and event pairs. So the compiler puts the bit stream for each new kernel it gets. So this is kind of the LUT we have. So each of this index corresponds to a set of instructions and set of operations to perform. So based on the current state, this particular instruction will be sent to the PE array. So each row is a 10-bit index made up of the state, the current state, the message ID, and some of the comparator flags. And output is a 48-bit instruction plus next state plus message data, message to the neighboring PEs. So yeah, this is quite helpful because we can map many kernels on a single silicon. So that's the compiler will flash it on the LUT. And yeah, it is bound to complexity because we have 10-bit index, so we can store 1024 state and event pairs. Now, just a small example to understand what exactly is happening inside the Canon. So we'll go through a sparse matrix multiplication. So yeah, this example we have earlier, we have seen this. So first we map the B matrix on the PE array. Here we have taken a 2x1 PE array, just for example, a small PE array, just 2 tiles. And we have mapped the first half of the B on the tile 0, then the second half of the B on tile 1. And yeah, so like that. And this is our A matrix. So we will look at the column of A matrix. So column 0, column 1 will go to the column 0 and column 1 of the B are here. So every non-zero from this part will go into the PE0. Every non-zero from the other remaining part will go to the PE1. So as you see, there are 3 non-zeros here. So this PE is more overloaded. This only has to do 2 operations, but here we have to do 3 operations. So that is the irregularity which we are going to see next, how the Canon tackles that. So step 1, we start with the multiplication. 5 goes PE0, 2 goes PE1, and k is equal to 1. So 5 times this and 2 times this, k equal to 3. So we have the results. Now we accumulate them to get the row 0 of C. Now step 2, we go to M1. M1 only has a work for PE0. It does not have work for PE1. So what will PE1 do now? It can sit idle, wait for M1 to complete, and then start along with PE0 for M2. But we don't like sitting idle, so we should do some work here. That's why what we are doing is we are storing the PE0 for M1 in the scratchpad as zeros, because we have all zeros. And then the PE row 1 can start computing for M2. So that's what we are doing. So we start multiplying by 4, and PE row 0 is still multiplying by 3. We have started with M2 in the PE row 1. And we store the result in the scratchpad. So this scratchpad is a FIFO, is a normal FIFO. So the result for M1 arrived earlier, so that should get out first. So that goes out as soon as we get the M1 result from PE row 0. And it adds up, gives the row 1 of the C matrix. Then we start with the remaining one, which we have here. And PE row 0 has to compute this. So 1 is multiplied and we get this. And from the scratchpad, we still have the value for multiplication of 4. So we just accumulate them. And here we get the C matrix. So that's how basically things happen. And this thing is actually called the asynchronous reduction. So we are not waiting for a particular row to complete. We can start with the next row if our work is done. So so this was a sparse matrix multiplication. We also have samples dense matrix multiplication. I mean, here we have both the A and B as dense, but the mask can be zeros or ones. So it samples the certain output. So that is also a sparsity in today's ML workflows. So Canon is also able to perform well on the SDDMM, and also in the structured sparsity cases, we have we can have 2:4 or n:2m sparsity. So basically, in n:2m sparsity, we see that for every m elements there are n number of non-zeros. So still we are fine with that, because because each of the PE row will get equal number of non-zeros. So that's why we don't have an imbalance here. So that's why we don't need a scratchpad. So I've just added a question in the quiz regarding this, so you can look into that. So now going to the evaluation. So this is our setup. 22 nanometer, 1 gigahertz, 8x8 PE arrays. We have int8 precision in 4 SIMD registers, and the PE SRAM size is 4 KB. 4 KB times each of the PE, which gives us the total memory as 288. Scratchpad is a 64-byte, orchestrator 8, 1 per PE row, and main memory is 17 Gbps bandwidth. And we are comparing Canon with these architectures that are there in the industry. So comparing the area first. So Canon actually has more area compared to the systolic arrays. Yeah, that's obvious because we are having an overhead of the generality. Because in Canon we have scratchpad, control, and routing logic. In systolic array is quite hardwired, and it is made up for a particular kernel only. So it does not have any scratchpad or routing logic. So we are actually 30% more on area compared to systolic arrays. Yeah. Now coming to the power breakdown. So basically we have 3 cases here. So first look at based on the sparsity of the workload. So when we have a very less sparse workload, that means that we have a regular input. So each of the PE rows will be balanced, and so mostly the FSM would stay in a FSM would stay in a max state because the irregularity is very low. So as we increase the sparsity, so some PE rows can get overloaded because of the irregularity in the input, and then the FSM starts switching more between these states, the flush, the accumulate, or the max states. And in S3, we can see that there are quite many transitions, almost 5 times more transition because of a lot of sparsity. So because of these transitions, we have more power consumption. So as you see, the systolic array is quite less power consuming, but as we go towards the sparsity from S1 to S3, we see that the scratch pad that is in the pink and yellow, they starts increasing up because we have more asynchronous buffer management cases happening in the computation. So talking about the performance, we see that in a normal generic matrix multiplication, systolic array and Canon are almost equal. So that's a good thing. And as we increase the sparsity from S1 to S3, we see that systolic array almost becomes half, but Canon is still having a good performance. Depending on the different sparsities kernels, Canon is holding its performance, but the other architectures are degrading. So systolic arrays, they collapse on sparse data, and it actually goes till when we have too much sparsity till 90%, it goes to 0.3x of Canon. And the ZED architecture, that is a sparse unstructured, the sparse accelerator for unstructured matrix multiplication. So it wins in the S1 zone because that is quite more or less more regular input. So it wins over Canon in this region. As you see, it's a bit high, but as we go to more sparse, it degrades, but Canon is not degrading. And so Canon outperforms all of the baselines in the window attentions. As you see, the Win1, Win2, Canon is outperforming there. Now talking about the performance and wattage, performance per wattage. So obviously here in the generic matrix multiplication, systolic array would be very efficient. So that's why you see that the performance per wattage is high compared to Canon. But as the sparsity increase, its performance per wattage degrades. So systolic arrays wins over Canon in the generic matrix multiplication, and also systolic 2:4 it wins on SPA on the kernel for which it is specialized, and Canon has to pay the cost of generality here. So as the sparsity increases, Canon starts winning. And ZED's full connected crossbar and decoders result in more power consumptions. So that's why you see that mostly this color is a bit down, because the ZED architecture has crossbar and decoders which are quite power hungry. So CGRAs, they just outperform in low data level parallelism scenarios because they are quite configurable, but with sufficient parallelism, Canon starts winning. Now, this is just the last part. So yeah, this is about the data memory size and the off-chip bandwidth requirements. So as you know, we are storing the B matrix of weights in the DRAM, and we have to fetch the tiles of B, the weight matrix, into the PE array. So we need some bandwidth for that, depending upon how much we have to fetch. This graph shows that thing. So for a particular SRAM size, say 72 KB, the sparsity increases. So when we increase the sparsity, the arithmetic intensity drops. Why? Because you are fetching a particular tile of B, but you have very less non-zeros to compute it. So to multiply the fetched tile with. So that's why your intensity drops and your required bandwidth rises. Bandwidth has to rise because there are you have to fetch the new tile of B again and again. That's why the bandwidth has to rise. So when you have a small SRAM, 72 KB SRAM, then you have to fetch again and again because you can't store all of the B content at once and reuse it many times. And when you have a large SRAM, say more than 576 KB, then you can fetch whole of the B matrix at once and just reuse it with the incoming non-zeros of A. So in summary, specialized architectures are efficient, but they fail on irregular kernels. Programmable ones are flexible but inefficient. Now Canon bridges this gap using FSM orchestrators and time-lapse SIMD execution. And Canon pays a small area and power overhead for generality compared to the specialized architectures, but it never collapses on irregular kernels. So yeah, some of the strengths and weaknesses now. So yeah, actually Canon performs really well across a broad spectrum of sparse kernels. So yeah, that's a good architecture. And so it tries to decouple the control from the compute. The orchestrator is the controller, and the PEs are just for computation. So that is a very good style of architecture. And we have a time-lapse SIMD, which is actually amortizing the control overhead. We have asynchronous reduction with explicit buffer management that really helps in tackling the irregularities. Then we have as we saw in the performance, in the sliding window attention, Canon was always high compared to the other architectures in terms of performance. And yeah, the results are quite honest, and wherever Canon loses, the author has accepted that. Some of the weakness now. So compiler is not end-to-end actually. So most of the compiler part is monitored by the human, and so there is manual selection of how the B matrix maps, how the data flow will go through the PE array. So that is more or less done by the human. Now we have 4 SIMD registers per PE. What if the inner loop is not divisible by 4? We are just wasting the SIMD registers inside the PE array. Now we also have a 30% area overhead, which might not be that good. So yeah, if you want to use Canon, you have to just have this trade-off of 30% compared to the systolic array. And so the workload is mostly tilted toward the tensor operation. Tensor operations are affine ones, so they are statically known. But what about the non-affine operations that the paper does not addresses here? So FSM scaling concerns. So here we have 6 KB LUT. We can store 2 to the power 10 state and event pairs. But if we want to increase the state event pairs, the scaling will increase because each PE will have a LUT. And the manual mapping bias is there in the results. Yeah, that is not in other architectures, but in Canon we are manually mapping that. So there can be a bias in the results. Now some discussions and possible improvements. So I just thought of this point that here we are considering A as only A is sparse and B is dense. What about if B is also sparse? Can you think of what should we do? So maybe we can add a sister orchestrator on the column. So for A, we had added the orchestrator on the rows. Maybe we can add orchestrator on the column as well. So yeah, what do you think? How this will impact, or do you have any other suggestions? Okay, this is what I thought. So adding a column sister orchestrator to the B to stream the B's non-zeros, it is quite similar to what we are doing with the A matrix. So yeah, it is architecturally symmetrical. So it can be helpful for sparse attentions in mixture of expert models because they are both A and B are sparse. But there is a fundamental asymmetric thing here, that when we only had the orchestrator for A, we were not bothering much about the control. But now we have to bother about the control as well, because we have to match the A and B orchestrators so that the correct elements get multiplied. So we have to have a control logic for that. So in conclusion, the idea is elegant, but operationally there is a trade-off between the control logic that we need to add for the B matrix. One more point can be the data type mix. So here all the results are for int8. So we have 4 wide registers for int8. What if we want floating point 16 or int16 precision? So yeah, anybody want to put their points? Like how can we do that, or how should we proceed with doing that? So the FSM is storing the instructions in int8 manner currently, but how can we do the support for other precisions as well? Yeah.
So I remember each P has like
Yeah. Yeah. Yeah.
So I guess it can transform directly to int16 by modifying the instructions that gets loaded.
Yeah. Yeah. Yeah, you're almost right. So so 4 registers can be converted into 2 registers of higher precision, like int16, or 1 register for FP16. So basically, that is the issue in doing that is we have to add a precision field in the LUT and a data type mux in the SIMD lane. So that is a natural extension of the architecture. But the problem is that the scratchpad and the entry width and the PSUM vectors all are designed for int8 arithmetic. So if we want to widen it for say FP16, we have to double the accumulator, half the number of PSUMs, and yeah, so we have to make some architectural changes. So it's not just a software update. We have to really do some hardware configurations as well. The last one is time-lapse SIMD is winning. So does it really wins at high PE count per row? So if the PE count is very high, so if one row has a large number of PEs, then the last PE will get the instruction very late. So there is a quite high latency here. So is that a good idea? Anybody has some thoughts upon how can we reduce the latency of instruction reaching the last PE? I've added a point here that we can have multiple orchestrators in between the row of the PE. So yeah, does anybody want to say anything about this point? Like what will happen if we add multiple orchestrators throughout the PE row? Okay, so yeah, it will actually help. So say a row has 8 PEs, so the last PE will get the instruction after 24 cycles. So if we have 2 orchestrators after 4 PEs, then we can reduce the latency here. But there is a catch again that multiple orchestrators, they break the Canon's core synchronization objective. So it will again increase the control overhead. So in conclusion, it's a trade-off. You have to put up the more control logic if you want to decrease the latency. So yeah, this is the conclusion. And so the takeaway is that extreme domain specialization is often unnecessary. With right control abstraction and right execution model, we can come up with a programmable architecture that approach specialized performance, and that's the gap Canon tries to fill. Yeah. So thank you, and I would open up the stage for questions or any discussions. Yeah.
I wonder if you can like explain again, like how it like detects 0 and like skip the 0.
Yeah, so that is done by the compiler actually. Let me go back to that slide. Yeah, so here, so that part is done by the compiler. So when the compiler sees this kernel, it will generate tokens like value 5 at k equal to 1, and then just row end. So 5 will go to the PE, and then the next token will go as a row end. So so the 5 gets multiplied, and then a row end arrives, so it flushes to the it flushes the PSM to the next row. So yeah, so as soon as here as well, it just sends 3 and then a row end. Here it sends 1 and then a row end.
So it's like done at compile time.
Yeah. Yes. So it depends on the kernel. Yeah.
Yes. Thank you.
Anything else you want to comment?
Sure. So in the last discussion slide, where we talk about the multiple orchestrators per row.
Yeah.
Wait, would you imagine how exactly would you sort of design that? Would you have essentially the two orchestrators, the multiple orchestrators in the same row, all executing the same, having the same FSM, or in that case, or would they do different things? And why would if they do the same things, would there really be a need for a synchronization? Or would it essentially be like two copies of the architecture working together?
But actually, if there was only one orchestrator, then say we add a orchestrator after PE4, that is starting from PE5 till 7, we have a different orchestrator.
Yes.
So now what is happening is PE5 gets the instruction at the very first cycle when the PE0 also gets the instruction.
Yeah.
So now we have to change the data flow a bit, because if we have one orchestrator, the data flow was accordingly that PE5 will get the instruction after 3 times 4 cycles.
Okay. I suppose you would just have to change a bit. You would say that when PE4 receives it won't propagate it to the next one.
That's right. Yeah.
Okay. I see.
That is a main point, and I think some more overhead can be maybe the synchronization part, because both of these orchestrator might execute in different cycles. So
why would they? Can you just control that at compile
that depends
time?
on how much how many non-zeros are there for a particular orchestrator row. So
yeah, I see. Okay, that makes sense. All right. Hey, thank you.
Yeah, thanks.
Thank you very much. So let's congratulate once more.
Thank you.
Downloading the new slides.
Was it long? Was it long?
It's took essentially the first half of the.
Ah.
I mean, we usually have like two
Let
presentations.
me get the
so
microphone.
Oh.
You just press like this. So
Like
there is,
this.
if you cannot touch, I mean, so after you speak, you can just mute it. So
Yeah.
once.
Sounds good. Do you want to test the mic or is it okay? Okay, okay. Let me know whenever you're ready. Yeah. Okay, so welcome back, everyone. For today's second session, we have Anika Gul. Anika is a second-year bachelor student in computer science at ETH. Her interests are in computer architecture and processing in memory, and she will present Darth-PUM. The floor is yours. Go ahead.
Yeah, thank you very much. So yeah, good afternoon, everyone. My name is Anika Gul, and I will be presenting the paper Darth-PUM, a hybrid processing using memory architecture. Starting with the executive summary, the problem is that analog processing using memory performs bulk matrix vector multiplication. However, many matrix-based kernels also need to execute non-matrix vector multiplication operations, which analog PUM can't perform. On the other hand, we also have digital PUM, which can perform general purpose computation in memory. So the goal is to combine both digital and analog PUM onto the same chip. And this is exactly what Darth-PUM is trying to accomplish, or what Darth-PUM does. So Darth-PUM is a general purpose hybrid ReRAM based PUM architecture that integrates both analog and digital PUM, and it contains an easy to use programming interface and low-cost support for flexible data bits. As a result, the performance improved by 15 to 60%, and the energy was reduced by 40 to 110% over an analog and CPU baseline. Now, as for the outline, first I will start with some background and a motivation as to why we even want a hybrid processing using memory architecture. Then I will explain Darth-PUM and also how it was evaluated in the paper. Then we will move on to the conclusion and the critique, and then finally we also have a discussion. So starting with the background. So processing in memory, or PIM, is the general idea of bringing computation closer to memory in order to tackle the problem of the memory bottleneck. There are two general types of processing in memory. The first one is processing near memory, or PNM, which is the idea of adding compute capabilities to memory by integrating conventional logic close to the memory arrays. On the other hand, we also have processing using memory, or PUM, which leverages electrical characteristics of the memory itself to perform computation. Darth-PUM only concerns itself with processing using memory. Actually, more specifically, it uses processing using memory with ReRAM. So ReRAM is, or resistive RAM, it's a type of a non-volatile resistive memory, and it stores data in the form of a resistive value across these crossbars in the memory arrays. And this value can then be changed by applying a certain switching voltage. Using ReRAM, we can do actually two different types of processing using memory. The first one is digital processing using memory. In digital processing using memory, we store 1 bit per device, and we can do Boolean operations between two input cells. Actually, with these Boolean operations, we can execute arbitrary functions, so we can execute any program using just digital PUM. However, one downside of digital PUM is that it is bit serial. That means that each bit of the output is computed sequentially. In the case of more complex operations, such as, for example, matrix vector multiplication, this can lead to a very high latency. So this is a downside of digital PUM. On the other hand, we have analog PUM. In analog PUM, we store multiple bits per device, and analog PUM can be used to perform efficient matrix vector multiplication. We'll take a closer look at that in a second. However, analog PUM also has some downsides. For example, analog PUM is quite susceptible to noise. So that means the results are often treated more like an approximate solution. So in effect, we either need to use analog PUM for situations where an approximate solution is good enough, or we need to find ways to improve the accuracy until we get a solution that is good enough. An additional downside of analog PUM is that we require analog to digital converters and digital to analog converters, because once we have the results, we want to convert them back to digital so we can then do further computation with them. So for now, we can take a look at how a matrix vector multiplication works using analog PUM. So we have this vector here and this matrix, and we want to multiply them together. So at first, we store the inverse of all the individual matrix values inside the crossbars of the analog array. as you can see here. Then we send the values of the vector across the word lines, which are then multiplied with the inverse of the values, with the resistive values of the crossbar, or multiplied with the values of the matrix. So in this case, for example, here we send a current of 2 across, and this is then multiplied by 5. Then in the next step, these currents get accumulated across the bit lines. So in this case, we have 2 times 5, and then we add that together with 7 times 8. After that, we have to use an analog to digital converter so that we can read out the values. And we get the end result, which is 66 and 67 as the result of our matrix vector multiplication. Now, as also mentioned before, analog PUM is not always very accurate, and there is a way to improve this, and that is bit slicing. So in bit slicing, when we have a larger n-bit value, we can split it into multiple smaller n over m bit values, where m is the number of bits that can be stored on a single device. So for example, in this case, we have 4-bit values in each of the matrix entries, and we can split those up into 2 separate 2-bit values. So for example, we take the first 2 bits of each matrix value and store them in one matrix, and we take the last 2 bits of each entry of the matrix and we store them in a separate matrix. Now, if we want to do matrix vector multiplication, we can multiply the vector with each of these matrices separately. And then afterwards, we have to shift the partial products based on the relative bit position, and then finally add them all together so we can get the final result. We can do something very similar with the vector. So instead of bit slicing the matrix values, we can also bit slice the input vector values. So now that we have seen some background, we will move on to the motivation. So why do we even want hybrid processing using memory? So as we have seen just now, analog PUM has limited flexibility. So up until now, it has been used mostly for domain or application-specific accelerators. On the other hand, we have digital PUM, which has enabled a wide range of general-purpose accelerators. However, digital PUM leaves a very large gap in performance for matrix vector multiplication style kernels. So the question is, can we combine analog and digital PUM in a way where we can get both of those? So we have more general applicability of digital PUM, but we also have the fast or the good performance of analog PUM for matrix vector multiplication. To further motivate this, we will take a look at an example. That is the Advanced Encryption Standard, or AES. That is a widely used block cipher that consists of 4 steps. And the first step is subbytes, which replaces each byte of the plaintext block with a byte from a substitution matrix. Then we have a second step, shift rows, which cyclically left shifts each of the rows. Then in the third step, that is mix columns, we do a matrix multiplication between the plaintext and the predefined matrix. And then in the final step, we execute an XOR operation between the generated key and the plaintext. We will now take a look at what happens when you try to do AES with first digital and then analog PUM and then finally hybrid PUM. So let's look at what happens when we do AES with just digital PUM. So we have just multiple digital PUM components without anything else. And we can do the whole algorithm using just digital PUM because digital PUM can execute arbitrary functions. However, the third step is a matrix multiplication. And as we have seen before, such a complex operation can have a very high latency when we use just digital PUM. So because this matrix multiplication is very slow, that means that digital PUM is not really a great accelerator for AES. On the other hand, we can try using just analog PUM for AES, or in this case, we have to use analog PUM in combination with a CPU because analog PUM can't perform all the steps of AES. In particular, we can actually use analog PUM only to accelerate the third step, and all the remaining steps have to be offloaded to the CPU. And it is quite bad to offload to the CPU because we will first of all have the data movement that we try to avoid when we use processing using memory. And additionally, the CPU has more limited parallelism as opposed to processing using memory. So this is also not really an optimal solution. So now the idea of hybrid PUM is that we use both digital and analog PUM at the same time. So we have both a digital PUM component and an analog PUM component. Now we can execute the third step using the analog PUM component, and we can do the remaining steps and the post-processing of the third step using the digital PUM component. And that's why we have the best of both worlds. We have both. We can both get the fast matrix vector multiplication of analog PUM, and we can use the flexibility of digital PUM for the remaining steps. And we also keep the increased parallelism of PUM in general. Now, there are still some things that we have to figure out with this. First of all, we somehow need to figure out how to actually coordinate between the analog and the digital domain. So how do we do that? And secondly, we also have to determine the amounts of analog and digital arrays that we use in each of these components. Actually, I want to talk a bit more about that second step. For that, I want to look at this graph. So here we look at the throughput for AES for different configurations of architectures. So on the very left, we have only digital PUM, and we can see what the throughput is for that. As you can see, there are two different lines in two different colors here. Those compare different logic families, but that is not important right now. So as I mentioned, on the very left, we have only digital PUM. And on the very right, we have a combination of analog PUM with a CPU. So these are the two configurations that we've already looked at before. And in the middle, we have various configurations of hybrid PUM. So on the more left side, we have a hybrid configuration that has a lot of digital arrays and only a few analog arrays. Then as we move to the right, we add more and more analog arrays and have fewer digital arrays because this is an isovariant comparison, so it's all for the same area. So on the very right, we have a lot of analog arrays, but only a few digital arrays. And as you can see, as we sweep through these different configurations, there's this sweet spot in the middle where we have the highest throughput. So the goal of a hybrid configuration or a hybrid PUM configuration should also be that we try to find this sweet spot. So in conclusion, if we want to create a hybrid PUM architecture, we have to carefully balance and coordinate between the digital and the analog PUM parts. This is actually exactly what Darth-PUM is trying to do. So Darth-PUM actually stands for Digital Analog Resistive Tiles for Hybrid Processing Using Memory. And the Darth-PUM architecture is made up, first of all, of a front-end controller. That front-end controller fetches and decodes instructions, and it also issues PUM-specific microoperations. This front-end controller is then connected to multiple hybrid compute tiles, which make up the backend. These hybrid compute tiles are actually made up of multiple other parts, and we will take a look at those now. So first of all, each hybrid compute tile contains an analog compute element where we can do analog PUM. It also contains a digital compute element where we can do the post-processing that we need for the analog PUM element, and we can also do the digital PUM operations that we have to do. Then in between, we also have a few auxiliary components that help with the coordination between the analog and the digital compute elements. And we will take a closer look at a few of those elements later. However, before we move on, I want to take a quick look at, once again, how a matrix vector multiplication happens using Darth-PUM. So once again, we have the vector and the matrix that we want to multiply with each other. And we want to do this matrix vector multiplication using bit slicing once again. However, this time we bit slice the input vector. So at first, we have the matrix values that are already in the analog compute element. And then we bit slice the input vector, and we place each of those bit values at the input buffer of the analog compute element. Then at each cycle, a 1-bit matrix vector multiplication happens. So we multiply each bit position of the vector with the matrix, and we thus generate a vector of partial products. These partial products are then transferred from the analog to the digital compute element. And in the digital compute element, each row or each element of the partial product is stored in a separate row. And this happens for all the bit positions of the input vector that we had. And once we have all of these partial results, we have to recombine them. Now we will also take a closer look at how this recombination happens. So here we have the partial results. So in row 0, we have the result of the first bit position of the input vector. In row 1, we have the second bit position of the input vector. And in row 2, we have the third bit position of the input vector. Now, the first bit position is already in the correct position, so we don't have to shift that anymore. However, row 1, to get the correct result, we actually have to shift it left 1 bit position. So we do that when we save it in a new row. Now, we actually have to do the same for row 2, because that is the third bit position. So to get it to the correct position, we have to shift it left twice. And we also store that in a new row. Now, Now to get the final result, we just have to add all of these shifted values together. So at first we add row 0 to row 3 and save that in a new row. And then finally to that new row, we also add row 4. Using that, we then get our final result. And as you can see, this is the correct result of our matrix vector multiplication. So now that we have seen a rough overview of how Darth-PUM works, I will take a look at a few more implementation details. Starting with shift units. So as we have seen, once we have a matrix vector multiplication, we have to shift and add the values to the partial results together. Now the problem is that the write, shift, and add operations can't be interleaved because they depend on each other. This means if we have a matrix vector multiplication, we have to do this for the partial vectors, and then you have to write, shift, and add all after each other, and this takes quite a long time. As you can see here, actually the post-processing takes longer than the matrix vector multiplications themselves. Now, this is quite bad, and this actually creates a bottleneck for this matrix vector multiplication. Now, Darth-PUM tries to solve this by adding multiple shift units. These shift units take the output of the analog compute elements, and they already shift the values to the correct position during the transfer from the analog to the digital compute element. So if we now take a look at what happens during the optimized matrix vector multiplication, we can see that the shift happens at the same time as the write step. That means we don't really have to add afterwards. As you can see, this is much faster than the unoptimized matrix vector multiplication. Another issue when transferring between the analog and the digital compute element is that analog PUM applies a row-wise input, but it combines it in a columnar direction. However, digital PUM drives the data column-wise, but computes row-wise afterwards. This means that this is exactly the transposed version. So any data that crosses between the analog and the digital element has to be transposed. Now we can do that using just digital PUM. However, that once again can increase the latency. So instead, Darth-PUM adds a transposition unit, which accelerates the process of transposing these values. So moving on. Some applications might want to dynamically adjust precision of the matrix vector multiplication, or they want to support larger matrix values. Now we can already do this using the bit slicing of the matrix values. However, that can be quite difficult. So instead, Darth-PUM supports this by using virtual analog cores. In these virtual analog cores, we logically combine multiple analog arrays into a single larger virtual analog core that we can then configure to support larger matrix values or better bit precision. So as we've also seen before, analog matrix vector multiplications are quite susceptible to errors or to noise. And analog PUM also tries to mitigate this by using a parasitic compensation scheme. This consists of both a remapping techniques, where the matrix values are stored using an alternate representation that can help to reduce the noise and the errors that we get. Additionally, it then does a post-processing error correcting code compensation. It has a post-processing error correcting code compensation factor that also helps with avoiding errors. This compensation actually leverages properties of the individual applications. For example, in AES, all the matrix values are either 0 or 1. So we can use that to then remap the matrix values to a representation where we have fewer errors. Now, as for software support, Darth-PUM provides both a library and full ISA support. So first of all, there is a library where we have both application agnostic calls. These are, for example, executing a matrix vector multiplication or setting a matrix. And we also have application-specific calls. For example, we have calls that are specific for AES. These calls are written in a way that they can be used by programmers even if they have very little or no knowledge of the underlying hardware of Darth-PUM. However, Darth-PUM provides also a full instruction set architecture. This allows programmers to directly manage the virtual analog cores on each of the hybrid compute tasks. This can enable people to write Darth-PUM applications for new applications, or also to include more flexibility and adjustments that the programmer can then decide themselves. So now let's take a look at how Darth-PUM was evaluated. in this paper. So Darth-PUM was evaluated for 3 different applications. The first one was convolutional neural networks, or ResNet-20 in particular. It was also evaluated for large language model encoders or transformers. And then finally, it was evaluated for the advanced encryption standard, or AES, that we already took a look at during the motivation. So currently, these applications often make use of application or domain-specific accelerators, such as specialized functional units. These are accelerators that only work for one specific application or in one specific domain, as opposed to Darth-PUM, which works in more general applications. Now for the methodology, the Darth-PUM chip was modeled using a modified version of Mastodon and CrossSim, and it was compared to 3 other configurations. The first one was a baseline configuration that consisted of a CPU with an analog PUM accelerator. And then it was also compared to digital PUM, which was just digital PUM, as the name suggests. And then finally, it was also compared to AppXL. Now, AppXL consists of different state-of-the-art application-specific accelerators. That means in particular that AppXL is different for each of the applications that Darth-PUM evaluates, or that the paper evaluates. Now, let's first take a look at the throughput of the different configurations. So here we have the throughput that is normalized to baseline, and we see the evaluations for AES, ResNet-20, large language model encoders, and then finally the average. In light blue, we have digital PUM, and then in purple, we have Darth-PUM. As we can see, Darth-PUM provides quite a significant speed up. On average, it is a speed up of 30.1 times over the baseline. And we can also see that Darth-PUM is significantly better than digital PUM in all cases. So as a conclusion, Darth-PUM significantly outperforms baseline and also digital PUM across all of our applications. However, the paper also compares Darth-PUM to AppXL. So now let's take a look at AppXL, which is here in red or in yellow for AES. And the picture is a bit different. As you can see in ResNet-20 and large language model encoders, the AppXL is still significantly better than Darth-PUM and also in the average. However, interestingly enough, for AES, Darth-PUM is actually much better than the AppXL, actually by 36.9 times better. That is quite a significant speed up. So now let's take a bit of a closer look at why Darth-PUM is this good at AES. For that, we will take a look at the latencies, or at the latency breakdown for AES. So on the y-axis, we have the percentage of execution time for the different steps of AES. So here we have the different steps. We have, first of all, data movement. Then we have subbytes, shift rows, mixed columns, and add run key, which are the 4 steps of AES. If we take a look at baseline, our baseline configuration, which is just CPU with an analog PUM accelerator, we can see that the 2 steps that take quite long are subbytes and mixed column. Also importantly, this is normalized to baseline, so baseline is 100%. Now next, we can take a look at digital PUM. And as you can see in digital PUM, it takes very long for the mixed column step. This is about what we expected, since we know that digital PUM can have a very high latency for more complex operations, such as matrix multiplication, which is mixed columns. And then finally, if we take a look at Darth-PUM, we see that Darth-PUM actually outperforms both baseline and digital PUM, as it has a much faster mixed column step than digital PUM. And it is also actually faster than baseline by 53.7%. So in conclusion, Darth-PUM is very good for AES. Now we can also take a look at the energy savings of Darth-PUM. Here you have a similar picture to the throughput. What is important here is that the y-axis is in a log scale. Now we can once again see that Darth-PUM significantly outperforms both baseline and also digital PUM for all applications. On average, it has an energy savings of 66.8 times, so that is quite good. However, once again, we can see that in the cases of ResNet-20 and large language model encoders, AppXL still outperforms AES. AppXL still outperforms Darth-PUM. However, in the case of AES, once again, Darth-PUM is actually better than AppXL. In the paper, there are actually even more evaluations, including an ISO area comparison to GPU, where the findings were that for the same area, Darth-PUM has both a higher throughput and lower energy requirements than GPU. The paper also takes a look at the impact of some device non-idealities and noise. And finally, it compares different analog to digital converters. There are two main different types of analog to digital converters. These are RAM analog to digital converters and SAR analog to digital converters. And the conclusion was that SAR outperforms RAM quite a bit by performance for slightly higher energy requirements. If you want to know more about that, you can either look at the paper, or I also have some graphs about that in the backup slides. Now we're already at the conclusion. So in conclusion, both analog and digital processing using memory continue to be promising solutions towards alleviating the cost of data movement. And Darth-PUM provides a complete hybrid analog-digital PUM system, which can be used to accelerate a variety of applications, all the way from machine learning to cryptography. And we have also seen in the evaluation that Darth-PUM can provide speedups of 59.4 times, 14.8 times, and 40.8 times over an analog plus CPU baseline for AES, ResNet 20, and large language model encoders, respectively. Are there any questions about Darth-PUM so far? If not, then I would move on to the critique. So I will start with some strengths of the paper. First of all, I think the approach of making analog PUM more generally applicable by combining it with digital PUM is very promising and also quite an elegant approach to this problem. Secondly, as we have seen in the evaluation, Darth-PUM performs significantly better than the baseline across multiple applications, showing that it is possible to use analog PUM in a more general accelerator, as opposed to specialized functional units. Then, as we have also seen in the evaluations, they were quite thorough. So they evaluated multiple parameters, and they compared multiple different configurations across 3 different applications. So it is quite a thorough evaluation. And then finally, the paper also explores potential expansions to Darth-PUM, for example, different approaches to improve accuracy even further. Now, I also have some critiques or some weaknesses of the paper. So first of all, while we have seen that Darth-PUM wins over baseline and digital PUM in both throughput and also energy savings, we have also seen that outside of AES, Darth-PUM has quite significantly worse throughput and energy efficiency than specialized functional units. And additionally, Darth-PUM still requires special hardware. It can't be run on commodity DRAM or commodity RAM. So this leads to the question of how much it is worth to actually use Darth-PUM over, for example, specialized functional units, or if the increased flexibility is actually worth the worse energy throughput and energy savings. As I've also mentioned before, the paper does evaluate accuracy. It does so for ResNet 20. And for ResNet 20, they find an end-to-end accuracy of 75.4%, which matches the accuracy of baseline and AppXL. So that is quite good. However, it only does this evaluation for one application. And also the simulator that was used for testing does not actually model all the possible error sources for Darth-PUM. So this means that the paper can't really report a comprehensive reliability for Darth-PUM, but instead it leaves this for future research. And then for my final point, I want to come back to the beginning and the motivation. So we had this graph, which as a reminder shows the throughput for AES for different configurations of digital, analog, and hybrid PUM. And we use this to motivate that we need to be careful with choosing the right amount of digital and analog arrays. And the paper also explicitly mentions that it is important to balance these amounts. And it also gives arguments for a balanced amount of analog and digital arrays inside of the hybrid compute tiles. However, the paper does not actually provide concrete numbers or a specific approach as to actually figure out what this amount then should be. So now we can move on to this discussion, where I actually want to continue with exactly this point. So how could we actually determine the amounts of analog and digital arrays in the compute elements of the hybrid compute tiles? For that, I first want to mention a few factors that could influence this decision. And these are also mentioned in the paper. First of all, we need at least as many analog arrays as we have matrices or submatrices in our application, because otherwise we would need to write to the multi-bit devices during the computation, and that can incur significant latency overhead. So we want to avoid that. Secondly, the fewer arrays that contain data at any one point in time, the less peripheral circuitry is required. So that means we want to try to limit the amount of arrays that we need so that we don't have to use as much peripheral circuitry. However, we also need enough digital arrays to actually store and process the output of the analog compute element, because otherwise we might have to stall until there is space in the digital compute element. However, if we have fewer digital arrays, we also need less peripheral circuitry. So as you can see, there are multiple trade-offs here. And these factors can also be more or less important depending on the application. For example, if one application only has very small or only very few array matrices, we might not need as many analog arrays as for a different application that has larger or more matrices. So that actually causes, so now I actually want to ask you, so how could we actually try to figure out the amounts of analog and digital arrays that we should use in the compute elements of the hybrid compute tiles?
We could just use. Which one? At the bottom. Oh yeah. We could try multiple models for the different applications to see which one is best, and then choose the one which performs the best over all the applications.
Something else? Someone else? Or? Yes, that's a very good point. That was actually also my idea. So the first approach that we could try is that we could create multiple variants of Darth-PUM chips, and we could try to optimize these for different applications. So we could have one Darth-PUM chip that is, for example, optimized for AES, and then we could just use a simulation to figure out how many analog and digital arrays we need for optimal throughput. Now, the downside of that is that now we have one that is more specialized for one application, so we could also just as well use a specialized functional unit if we are going to use it mostly for that application. And as we have seen, Darth-PUM still performs somewhat worse than functional units, except in the case of AES, so maybe that wasn't the best example. But this kind of leads to the question, okay, why not just use specialized functional units then? I think you also mentioned that we could just try to figure out a configuration that works well for all of these applications, so it's somewhere in the middle for all of the applications. Now we have more of the flexibility, but it also means that we have worse throughput than if we try to specialize more for one application. Then the final one is something that I thought could be in the middle. So we could try to figure out which of these applications is the most important or which one we are going to use the most. And then we could try to optimize proportional to how important the different applications are in our use case. Good. Okay. Then I want to move on to the next discussion point, which is what other applications could also make use of Darth-PUM. So in the paper, we looked at Darth-PUM for 3 different applications. Those were convolutional neural networks, large language model encoders, and AES. So what other applications could also benefit from Darth-PUM? Does anyone have any ideas?
Well, with convolutional neural networks, we could use that for machine learning and try to make advancements there.
Mm-hmm.
I can add a bit more. Maybe in any application that shows similar patterns to matrix vector multiplications, right?
Mm-hmm.
Or workloads that have matrix vector multiplications plus some other scalar properties that you can run digital PUM.
Mm-hmm.
That would be a way to generalize
maybe. Yeah. Okay, that's kind of my point. So Darth-PUM can be useful for any application that contains matrix vector multiplications that don't have very high accuracy requirements. These could be, for example, in machine learning, as you mentioned, but there could also be applications in analog signal processing or for example, in scientific computing. Actually, I want to continue a bit more in this direction. So could the analog devices in Darth-PUM actually be used for operations other than matrix vector multiplication? Okay. Or I think there's somewhere.
I think maybe it can kind of do any matrix-like thing, like anything that can be generalized to matrix multiplication, such as like data shuffling, kind of, or like weighted average or filter or things like that.
Mm-hmm. I mean, we can use Darth-PUM or the analog arrays for pretty much any multiply and accumulate operations. So you're right that there is more potential there.
Yeah, so in general, I see that since this is usable on matrices, you can basically perform the same operation on multiple data units simultaneously. So this could basically be able to do some operations which a vector processor could do or a GPU could do, performing the same operation on multiple data units simultaneously. That would be a more generic answer. In fact, I can't think of any specific applications other than matrix vector multiplication. So yeah, that's the answer.
Yeah. So there is actually some research into using analog arrays for other things. So in particular, there is some research as to using analog devices as content addressable memory. So content addressable memory compares an input search word against all rows of stored words in a highly parallel manner. And this is actually used in various situations, for example, in tree-based machine learning. It is also used in convolutional neural networks or in dense neural networks. And it can also be used for transformers or, for example, in network routing. Up until now, this has been mostly implemented using digital PUM in SRAM. However, that can lead to quite high energy or high power and area requirements. And there is actually some research to show that analog PUM can be used to reduce power and area requirements. So it could actually be an interesting direction to look at how to possibly implement content addressable memory in Darth-PUM. Yeah.
But if you use that thing in it, like for CAM, then probably the accuracy be the matter in this case, because like if you use the analog thing, then the accuracy goes down and can be also the minus point in this case.
Mm-hmm. Yeah, I think accuracy is always a bit of a concern when we use analog arrays.
So yes, one potential way, which also the paper looks at a little bit, right, with whether they can retain accuracy with their operations is one possible way. Plus, some of these workloads, for example, with machine learning models, there could be layers that are not that susceptible to errors. So potentially you could run those layers on these lossy circuits. So this might need some profiling, but maybe it's possible to still run them even if they're, let's say, not 100% reliable. But of course, there is need for research in making these more reliable, I think. Just to add on Annika's answer.
Thank you.
Yeah. Does that answer your question?
Yeah.
Okay. Anybody else?
Okay, then I guess we can move on to the last discussion point, which is actually about reliability. So as you have seen, analog PUM operations have relatively low precision. So in situations where we need matrix vector multiplications with higher accuracy, how could we actually implement those? Okay, if there are no ideas, then I will start. So first of all, if we have matrix vector multiplications that have very high accuracy requirements, we could just use digital PUM instead of analog PUM, because then we don't have the downside of lower accuracy. However, the problem is that we have much higher latency. And we also, if we always only use digital PUM, we could just as well use only digital PUM instead of Darth-PUM. However, we could then try to decompose applications or operands depending on how important they are. So if we have one matrix vector multiplication where it is very important that we have an accurate result, we could do that using digital PUM. But if we have a different matrix vector multiplication where we don't have as high accuracy requirements, we could try using that. We could still do that using analog PUM. So in that case, we could still use Darth-PUM even in situations where you sometimes have high accuracy requirements. There are also other approaches. For example, we could try to mix the ReRAM with a different memory technology that has higher accuracy. Then we could do those matrix vector multiplications with that. However, that could, for example, make manufacturing more difficult because we now have multiple memory technologies. Finally, we could also just try to add more error mitigation techniques to improve on that until we have the accuracy that we require in this application. Are there any questions about that? Okay, then that means I am finished now. So if you have any questions, you can ask them now.
I have a question about the performance compared to the upsell and the baseline. So I think the goal of Darth-PUM is achieving a general purpose, a better performance, and it showed that it was outperformed compared to baseline, but it wasn't. It had a worse throughput compared to upsells. However, I'm curious that why it was only better in AES and why it was not in other cases. So how did Darth-PUM achieve a better performance in AES?
Okay, so I think I'm not quite sure, but I think the APEX cell that was used for AES is actually quite different compared to the APEX cell for other applications. And I think a big factor is also just that AES is very well suited to Darth-PUM.
So I think that in other cases it was impossible to outperform compared to upsells, but like the property which made the Darth-PUM better in AES would be like a insight for like other general cases. So I was curious about the reason.
That could be possible. I'm actually not sure about that.
Okay.
Any other questions? Okay. Yeah. Well, I think thanks for the nice presentation. Both you and the previous presenter did a great job. This is very interesting work, I think, and I think you identified the strengths and weaknesses really well. One issue is applicability. Like, is this applicable to DRAM?
No, it is not.
Not at all.
I don't think so, because we have the analog PUM operations and we need those crossbars that we don't have in DRAM as well.
That's basically building on the matrix vector multiplication primitive in the crossbars. That's good food for thought for maybe enhancing DRAM to do something like this. All right. Anybody else think? All right.
So then I think we're done. Congratulations. Thank you. So now we're going to switch to the third presentation. So let's have basically a 5-minute shift to the next one. Okay.
Download the slides for him.
Yes, we need to do this. Who's the mentor?
And
It's almost 6, right? So this lecture will be.
It's okay. We're gonna.
Oh, it's okay.
Yes. So maybe you can find it in the.
Sure.
This one, you can wear it. Yeah. This is okay for you?
Yes.
And you're ready.
Can I just okay. Yeah.
Thank you.
Thanks.
No worries. Thank you. Start in a bit. Okay, so guys, I think we can continue. So, so now it's unmuted. Then you press 1, you mute it after it.
So our last presenter for the day is Tejaswar, who is a first-year electrical engineering master's at ETH. And his interests are towards computer architecture and VLSI design, with a focus towards heterogeneous computing systems. So Tejaswar, the stage is yours.
Thank you. So hello everyone, I'm Tejeshwar, and I will be presenting the work which was presented in HPCA 2026 actually. It's a very recent work. So the memory processing unit, a generalized interface for end-to-end in-memory execution, right? So yeah. So what are the problems and challenges with the existing PUM systems that the paper highlights? So to start off with, all these PUM systems that are there, that are under research currently, they have different data paths, they have different hardware architectures. And because of these unique hardware architectures, there is not one unified programming model for all of these. And also the PUM hardware as it is cannot handle control flow operations. So they are dependent on the CPU to handle control flow operations, right? So along these lines, what's the goal of the research paper? So to develop a hardware agnostic programming interface to improve programmability with better software tools and a common ISA, and finally to enable end-to-end execution on PUM. So both compute and control flow instructions will now run on the PUM hardware. And so what are the paper's contributions? So to satisfy these goals, the paper introduces the memory processing unit framework. So it has three main components. Firstly, it proposes some generic hardware abstractions which are common across all the microarchitectures. And it proposes something called the Ensemble programming model on top of these hardware architectures. And it proposes a common MPU ISA and an easy PIM assembler, which makes programming much more easier now. And finally, it enables in-memory control flow with hardware and software support for instructions like jumps and masks. And how are all these things being tested? So they are tested on the MIM-DRAM, racer, and duality cache PUM data paths. And they've been tested with 21 benchmarking kernels and 3 end-to-end applications. So significant improvements were actually noticed across all these comparisons with respect to GPUs and the baseline PUM data paths. So moving on, I'll start off with some background on what processing using memory is. So PUM is basically a computational paradigm which tries to perform computations directly inside the memory arrays, and it does so by harnessing the electrical interaction between these memory cells. So to give you two quick examples, you can take a look at the image to your left. So here you're seeing 3 DRAM cells, and when I activate all 3 of these rows, this mechanism is called the triple row activation mechanism. So when I activate all 3 of these rows, a majority gate operation happens along the bit line. And so here you see that A has 0, B has 1, and C has 1. So the bit red will be obviously 1 here. So that's how a bitwise operation happens on the DRAM cells. And the image on the right shows you a similar case with the resistive RAM cells, where a voltage is applied across the column lines, and it induces a current flow which goes through the row and reaches your destination cell, and you can accordingly store a 0 or 1 in the destination cell. So that's basically how you emulate a bit operation in resistive RAM cells. So now that we know about the bitwise operations, let's look at something on a more system level. So this is MIM-DRAM. This is actually Safari's work. So MIM-DRAM is a PUM data path built on top of DRAM cells. So the smallest unit of compute here is the DRAM mat, which is nothing but a collection of different rows and columns of DRAM cells, and multiple such DRAM mats put together with 2 entities called the microprocessing engine and a scoreboard, which are monitoring these DRAM mats, together form a single subarray, and multiple such DRAM subarrays together form the entire DRAM module itself. So that's how the MIM-DRAM's hierarchy has been organized. And there is something similar called the racer, which is a PUM data path designed using resistive RAM cells. So here the smallest unit of compute is called a tile, which is a collection of rows and columns of resistive RAM cells. And 64 such tiles put together with single column registers in between form a pipeline. And 64 such pipelines along with the pipeline control circuitry forms a cluster. And multiple such clusters with interconnects together form the entire racer chip. So that's the PUM data path called racer. And so we have seen a couple of existing PUM architectures. So now what are the limitations with these architectures? So firstly, there is no proper execution model, meaning you cannot like design and schedule parallel work easily with these architectures, and it is difficult to monitor and manage hardware utilization. And weak programmability. So you don't have explicit tools like CUDA support or OpenMP for PUM hardware at the moment, and they don't support control flow instructions. And because they don't support control flow instructions, they are dependent on the CPU to handle control flow instructions, which creates a lot of overhead. And finally, poor portability. Any software binary I write for MIM-DRAM cannot run on Racer, and vice versa, right? So how does the paper address all these issues? So the paper basically introduces something called the ensemble-based programming model, which is built on top of the common hardware abstractions, which we'll be seeing very soon. So this is how it resolves the problem of the lack of an execution model, and improve programmability by introducing a common ISA and the software support with an assembler, and hardware and software support for control flow instructions. So now end-to-end execution is possible on your PUM hardware itself. And finally, portable binaries. So now that you have a common ISA, which can extend across multiple microarchitectures, and you have common hardware abstractions, you can basically have portable binaries. So I'll first give you a conceptual overview of what the paper is trying to achieve before I delve into the hardware and software specifics. So The memory processing unit basically tries to address these 4 design considerations. I'll take you through one by one in the next slides. So yeah, expressing flexible degrees of parallelism. So if I want to perform one single operation on some data units within a DRAM mat, I'll do a triple row activation. I'll store the result. As simple as that, right? I mean, I'll do a triple row activation. I'll perform the bitwise operation and I'll store the result. Simple. But what if I want to perform the same operation across like different data units stored in two different DRAM mats parallelly, right? In such cases, I would want to do triple row activation on both of them, perform the bitwise operations, and store the result, right? So when I'm writing program for such an operation, I'll basically say I'm grouping these two DRAM mats and I'm going to call them an ensemble of two DRAM mats. So with an ensemble, I can basically do parallel execution across 2, 3, or even n different data units stored across n different DRAM mats. So that's the idea behind an ensemble. So with this, I can express flexible degrees of parallel operations. And program execution compliant with hardware constraints. So first, what are these hardware constraints? So take a DRAM mat. A DRAM mat basically has multiple rows and columns. So if I engage each and every one of these DRAM cells in some sort of bitwise operation, I'm going to be discharging and charging a lot of capacitors. Now this will have two implications. Number one, there'll be a lot of current flowing around. And number two, this is going to generate a lot of heat. So because of all this current that is flowing around, and because I'm charging a lot of capacitors, which is going to draw power from my power line, there'll be a voltage drop. So because of this thermal and this power implication, I have to restrict the number of DRAM cells I am activating within a DRAM mat. So those are the hardware constraints here. So because of that, just to illustrate this, I'm going to set up the rules saying, in a given setup, let's say I have 4 DRAM subarrays, each of them having 4 DRAM mats. Only 2 active DRAM mats are allowed in one subarray, and only 1 active operation in one DRAM mat to remain conscious about the thermal and power limits. So say in subarray 0 and 2, I already have 2 active DRAM mats. So if I want to schedule my ensemble of 2 DRAM mats from the previous example, I would do it like this. I would put it in the subarray 1 and subarray 3, as simple as that. Now let's take the same setup. But this time I have subarrays 0, 1, and 2, which are fully occupied, and I only have empty space in subarray 3. But then I cannot schedule my ensemble of 2 DRAM mats because I need to schedule both of them simultaneously for parallel execution. So in this case, I'll have to stall until sufficient hardware units become available. So that is about execution of program in compliance with hardware constraints, and control flow inside the PUM hardware. So frequent off-chip requests to the CPU create a lot of overhead. So the flow basically looks like this. Like a conditional statement is encountered, and then there is some sort of PUM comparison, there's some sort of comparison which happens in parallel on the PUM hardware. And then the result of this comparison and the actual data gets sent to the CPU. The CPU does the computations, sends it back to the PUM hardware. PUM continues parallel execution. So it's a very tedious process. So how do we resolve this? So we basically provide support for scalar execution and lane masking on the PUM hardware itself so that we are not dependent on the CPU anymore. So scalar execution, meaning they are like these simple operations which happen on individual elements, like, a loop increment, like something like I++, or like checking if X is greater than 5, something like that. And lane masking is basically that. So you see that in a vector register, I have multiple lanes. Each lane will store one element. So if I perform a condition and if I decide that I only want to operate on certain elements in a lane and not all of them, I will accordingly set the mask register bits for those lanes and enable or disable specific lanes. So that's what lane masking is for. It allows us to perform conditional operations. And yes, with this support, we are basically eliminating these 3 blocks from this entire flow. So everything happens on PUM hardware now. And finally, maximizing the portability of MPU binaries. So we'll have to write code for each of these microarchitectures separately. That's the problem. But with the common ISA and with a universal decoder bridge to convert these ISA instructions into micro operations which the hardware can understand, we can actually resolve this issue and have common binaries for all of these microarchitectures. So that makes us, that enables the creation of portable software binaries. So that was a more or less a conceptual overview of what the paper tries to achieve. So now let's delve into the specific hardware details. So what are the hardware abstractions that this framework basically requires? So the MPU framework introduces 2 hardware abstractions. The first one is called the vector register file. As the name says, it's a register file. It contains multiple vector registers. And a register file holder is a group of multiple VRFs, right? So the RFH, the register file holder, basically has some kind of a safety and monitoring purpose. So it keeps track of the states of the active VRFs under its purview and notifies this to the scheduler, and accordingly tasks can be scheduled on the hardware, right? To ensure that thermal and power limits are not violated. And to give you a more realistic example, this is our MIM-DRAM system again. So in MIM-DRAM, one vector register corresponds to one row of the DRAM mat, and multiple such rows form multiple registers within a DRAM mat. So one DRAM mat is one vector register file, and one register file holder is mapped to one microprocessing engine, which is essentially going to monitor all the DRAM mats under its purview, right? And similarly, if you look at Racer, in Racer, we follow a bit striping mechanism where multiple bits are stored across multiple tiles within the same vector register. So one vector register itself extends across multiple tiles. So one entire pipeline with 64 tiles together forms your vector register file, and your register file holder is one entire cluster, which is the group of VRFs. So 64 pipelines together, which is one cluster, and that is mapped to one RFH in the Racer. And duality cache. So this is new. We haven't seen this before. So duality cache is nothing but an SRAM based PUM data path. So in this case, one vector register corresponds to one SRAM, one row on an SRAM subarray, and one vector register file is an entire SRAM subarray. And the register file holder is basically one issue window. So one issue window has a lot of SRAM subarrays under its purview, and it issues instructions to execute on these SRAM subarrays. So that's the idea. So the key takeaway from this section is that you see that the underlying hardware is different in each case, but there are structural similarities which allow us to form similar abstractions across all these architectures. And on top of this, we'll create frameworks to write some software, which is what we'll look at in the writing an MPU program section now. So I had mentioned something called ensemble programming model. So I'll talk about the ensembles now. So the first type of ensemble is the compute ensemble. So you can think of an ensemble as a simple thread which will allow me to execute one operation on multiple data units at the same time in parallel, basically, right? So for example, I'd like to direct your attention to that orange block with a simple code snippet. So the compute ensemble has three sections. The header basically tells you which VRF do you want to operate on. So each VRF contains some data. So I basically define which VRF I want to operate on and in which RFH is it located. And the body basically tells me the address, the body basically tells me the operations which I want to perform on each of these VRFs registers. And the footer is just a flag that says the computation is done. So a small illustration is given on the left. So let's take the add operation. So across all three VRFs, I am now adding register 0 and register 1, and I'm storing the sum in register 2 parallelly. So this is what a compute ensemble would allow you to do, right? And so the other type of ensemble is the transfer ensemble. So that handles the compute. This handles the movement of data across different VRFs. So to give you an example, you can look at the code snippet on the right top. So you see that the header defines the source and the destination RFH between which I want to transfer data. And the mem copy instructions in the body basically tell like from which register and which VRF should I pick the data in source, and to which register and to which VRF should I write the data to in the destination. And the footer basically tells you a move done flag. So that is a transfer ensemble. So now I've shown you simple examples of how you can write a compute ensemble to perform some computation and some transfer ensemble to move data around. So what happens to this code after you write this? That is where the assembler comes into the picture. So the assembler, so in this case, you are allowed to basically define code in some sort of a high level syntax, and then it gets converted into MPU ISA based instructions with the help of this assembler. And this assembler offers some, so this entire framework offers you some support for and while loops with the conditional jump instruction. You have if else condition support with masking instructions, and you also have subroutine calls support with jump instructions. And with all this, you can basically write program and ensure that it the end-to-end execution happens on the PUM hardware itself. You don't have to go back to the CPU again. So we'll keep coming back to these 2 points multiple times because that's like the ultimate goal of the paper. And the paper actually details out all those support items in detail in terms of software implementation. So I'm not going to cover everything in detail. So just to give you a simple example, I've taken one single case. So for dynamic loops, so I'd like to direct your attention to this simple for loop over here. So the for loop is translated to the MPU ISA based instruction code over there on the right. So you see that I'm initializing my loop counter, which is R0, and then I'm doing a comparison between R0 and R1. I'm adding, I'm performing an addition operation, and then I'm incrementing my loop counter. And then there is a conditional jump, which loops back to the start of the loop again. So that is how your dynamic loop code gets converted into MPU ISA based code by the assembler. And another example that illustrates how masking happens. So you can take a look at the code on the right, which shows you a simple while loop. So the condition is if x of y is greater than or equals 5, I'm going to keep decrementing the number by 2. So you see that among the 4 lanes in the register, only the first 2 lanes in the first row satisfy the condition. So the mask register is 1100. And then eventually, as the values keep updating, the mask register also updates, and the loop keeps executing until all the mask bits become 0. So that is about masking. And yes, so now I've given some overview, I believe, about the hardware abstractions and how to write software on top of these hardware abstractions. So now let us try and understand how this hardware and software interacts, right? So this is what the control path hardware and the runtime are handling basically. So over here, there are 3 main units that you should understand. So the first one is the precoder. So the precoder has 2 subunits called the instruction storage unit and the fetcher. So the ISU stores all the code, basically the instructions that you write in your code are stored in the ISU, and the fetcher fetches these instructions and then checks if it is a part of a compute ensemble or a transfer ensemble. If it's a part of a compute ensemble, it goes to the compute controller. If it's a part of the transfer ensemble, it goes to the data transfer controller. So the most important out of all these 3 is the compute controller actually. So I would like to spend some more time on it. But before I enter the compute controller in detail, I would like to cover 2 more small entities which we should understand to properly grasp the compute controller's use case. So the first one is the playback buffer. So think of the playback buffer as a simple FIFO queue-like structure which receives instructions and queues them, and then whether the instruction can be issued or not. So that decision is taken based on the inputs given by the scheduler. So the scheduler basically checks the RFH and sees if the hardware units are available to issue instructions, and accordingly directs the playback buffer to issue instructions. So to give you a simple illustration, let's take this simple compute ensemble. And I will say that this, so I'm trying to perform some operations on RFH2 VRF1 specifically. So let's say that this is VRF1 with 6 registers. So my add operation between R0 and R1, and I'm going to store the result in R2, that gets scheduled first. And now I cannot run the same, I cannot run the multiplication operation on the same VRF because we have our condition, which is only one operation can be actively happening in a VRF at a time because of the hardware constraints, the thermal and power constraints. So the playback buffer will pause here. And after the add operation is done, there is something called a sequence replay which happens. So basically the playback buffer iterates through all its instructions and checks where it had paused. So then it then identifies that the pause had actually happened at the multiplication instruction. So it does the replay and it resumes from the multiplication instruction, and then the multiplication instruction is issued to the hardware and it executes. So this is basically the operation of the playback buffer. And the second entity that we should understand before entering the compute controller is the I2M decoder, the instruction to micro-op decoder. So here the playback buffer does not send the instructions directly to the hardware. It sends it to the I2M decoder, and the I2M decoder breaks down these instructions into M different micro operations. So to give you an example, you can take a look at the table below. So the add operation is broken down into a series of XOR and AND operations actually, right? And one interesting thing I'd like to point out here is that you see the first 2 operations, the XOR and AND on the template lookup box over there, have A and B mentioned over there. So that is because this is a template. So what happens here is you have the instruction template readily available. So all you have to do is you just have to fill in the registers of the the register addresses for the 2 operands in the template, and the template as a whole gets dispatched to the hardware, right? So that is the idea behind the recipe table and the template filler. So the recipe table holds the templates for all these instructions, and the template filler simply fills in the register addresses, and with the register address, the whole instruction gets sent to the hardware. So that is about the instruction to micro-op decoder and the recipe table. And now let us move into the compute controller. So we'll start off with the activation board. So the activation board is a unit which basically maintains a lot of flags which tell you which are the active VRFs in an RFH and whether the RFH is actually within limits or at limits. So this information is sent to the scheduler, and the scheduler tells the playback buffer, if the RFH is within limits, send instructions to the I2M decoder. If it is at limits, then stall, you will not dispatch any further instructions. So that's the idea behind the compute controller. And this is the entire this is the entire control path hardware. So you see the process begins with the precoder. From the ISU, the instructions go to the fetcher, and from the fetcher, it either goes to the compute or the data transfer controller. In the data transfer controller, so we define the source and destination RFH in the transfer ensemble, if you remember. So based on that, a target map is created with the source and the destination addresses, and the data to be transmitted is loaded onto the data buffer and dispatched. And if it's a compute ensemble instruction, it goes to the compute controller, and the instruction is queued in the playback buffer. And if the scheduler allows for the scheduling of tasks because of the hardware availability, the instruction goes to the decoder and then eventually reaches the hardware, which is the RFH and the VRFs essentially. So yes, so we have essentially covered different aspects of the MPU now. So I would like to move into the evaluation section. So to start off with, the MPU augmented PUM data paths and the baseline PUM data paths comparison is shown here. So we can see that on an average, we can expect like a 3x, I mean, we are able to see a 3x efficiency improvement, energy efficiency improvement, and roughly a 50% performance improvement on an average. And one interesting observation here is that there are 4 different types of kernels here: the basic, branch focused, stencils, and the complex kernels shown at the bottom of the slide. So the improvement over the basic and branch focused kernels is marginal, whereas the improvements over the stencils and complex kernels are quite significant. So the reason here is that the basic and branch focused kernels, they do not have a lot of irregular data movement or a lot of control flow instructions. So the baseline itself is able to do a very reasonable job there. So the improvement that is given by the MPU is not so significant. Whereas in case of stencil and complex kernels, there are a lot of conditional statements and a lot of irregular data movements involved. So the MPU augmentation actually shows significant improvements in these 2 kernels, I mean, in these 2 scenarios basically, right? And when we compare the MPU augmented data paths with the GPU, the results are a bit volatile. We are able to see improvements, but on different scales. And one interesting point here is that in the complex kernels, there are some cases where the GPU outperforms the MPU augmented data path. So there is actually a solid reason behind that, which I'll come to in the next slide. So yes, like first I'll cover the end-to-end application analysis now. So there are 3 end-to-end applications which the which the system is evaluated upon. So LLM encode, Black-Scholes, and edit distance. So the MPU augmented data path outperforms both the GPU and the baseline PUM data paths in case of LLM encode and edit distance. But in case of Black-Scholes, we see a performance dip with respect to the GPU. So now we actually see a dip in performance with respect to Black-Scholes and the complex kernels from the previous slide. So the reason being, these complex kernels and this specific Black-Scholes application, they both involve a lot of intensive mathematical operations basically. So when the MPU encounters such operations, it takes a more conventional route. It breaks down these instructions into smaller micro operations and it schedules them on the hardware, which takes a lot of time and a lot of latencies involved. But the GPU has got specialized hardware to handle all this. So the GPU has an unfair advantage over there. So that is why the GPU is able to beat the MPU augmented data path. But this is not a very solid limitation at this point, because this could be a future scope. In future, if we are able to come up with a workaround on the PUM data path for this, then PUM can hands down beat the GPU is what I believe. So yes. So now we had a performance analysis. Now let's look at something on the programmability side. So initially, without the EasyPIM assembler and the MPU ISA, like the programmers had to write a lot of codes with separate instructions for every low-level operation. So the number of lines of code that were written on the baseline were so large, but with the EasyPIM assembler and with the MPU ISA, the number of lines of code to be written have come down significantly. So that is a major improvement step in terms of the programmability. And finally, we spoke about the overhead that is occurring because of the CPU PUM interactions. So to quantify that, the paper classifies the entire compute operation into 3 sections: the MPU computation, the inter-MPU communication, and the off-chip communication, right? So if you look at LLM encode and Black-Scholes, the integration of MPU basically eradicates the entire off-chip communication part and brings down the execution time by roughly 20 and 60% respectively. Edit distance is a bit peculiar. So edit distance as an application has a lot of conditional statements, right? So when you execute this on the PUM baseline, it almost always waits for the CPU to send instructions, because a lot of these if conditions and else conditions are sent back to the CPU. So it almost always waits for the CPU to send instructions and then begins PUM execution. So that basically means that the baseline is giving horrible results with respect to edit distance, which is why you're able to see 100% improvement on integration of PUM. On integration of MPU into the PUM data path. So it is not an exaggeration. It is just that the baseline's performance is very poor. So yeah. So that was the evaluation section. And to conclude, the paper solves the execution model gap with the ensemble-based programming model and the hardware abstractions. And it also introduces the MPU ISA and the assembler. And we have actually seen the programmability, like the ease of programmability after introduction of these two on the MPU augmented data paths. And now we have also seen the quantification of what the CPU interactions does in terms of overhead and how eliminating the CPU interactions will significantly improve our performance. And with the control flow instruction support, that has been made possible. And finally, the overall takeaway is that with these hardware abstractions and with this common ISA, you can now perform end-to-end execution of tasks on the PUM hardware itself. And oh, sorry, my bad. So yeah, there is also this point about portability. So with these abstractions and the common ISA, you can now run the same binary on multiple microarchitectures. Yeah. So paper critique, yes. So regarding the strengths, so the first one being comprehensive evaluation. So there are 21 benchmarking kernels in 3 end-to-end applications on which the system has been tested. And the paper also like explicitly justifies the non-ideal cases with reasoning. So that adds more credibility to the work. And secondly, this is an architectural novelty that the paper introduces. So in conventional GPUs and vector processors, you basically perform the computation first, and then you perform lane masking in case of predications. But this specific implementation first disables the unwanted lanes and then performs the computation only on the necessary data. So instead of performing all computations and then disregarding the unnecessary data, we straight away perform computations only on the necessary data. So this is a more efficient way of implementing the same thing. And yes, so the CPU overhead is quantified. So instead of plainly stating that interactions with the CPU and PUM can actually add significant overhead, the paper quantifies this and uses that as a strong motivation for introducing the MPU framework. And finally, this is something I find to be very nice about the paper. So instead of literally creating a whole new microarchitecture, a whole new ISA and everything from scratch, the paper thinks about how it can improve upon the existing systems itself. So that's something nice that the paper has done. And in terms of weaknesses, so EasyPIM is still an assembler and not a compiler. So even though you are allowed to write high-level syntax code to a certain degree, you still need to have a very good understanding of the hardware. So hardware-aware programming is still not fully eradicated. And secondly, thermal scheduling limitation. Yes. So we saw that even though there are like roughly 16 different DRAM mats across 4 subarrays, I could only use 8 of them. So a lot of my raw hardware is literally having to stay idle because of my power and thermal limitations. So I'm not fully utilizing my hardware compute power. So this is actually acknowledged in the paper, and I mean this is actually not acknowledged, but my bad, sorry. So this is acknowledged, but this is not addressed in the paper. The solution is not explicitly stated in the paper. And I believe with better cooling systems and with better thermal aware designs and with better power distribution, in fact, we can overcome this. So yes, with that, I would like to enter the discussion, but before I start the discussion, do you have any questions? There is. Yeah.
Thank you for the presentation. So I have a few questions.
Yes.
Can you change the ensemble size?
Yes, you can. So you can group n number of DRAM mats together to perform the same operation across n different data units. So that's how you would express flexible parallelism. Yeah.
Yes. And also why is one register file assigned to one mat directly? Wouldn't that make it not possible to parallelize between mats?
No, one register file is not assigned to one mat. One register file is basically one register file holder has multiple DRAM mats under its purview. Wait, are you talking about the vector register file or the register file holder? There are 2 entities.
I think it is the vector register file.
Okay.
Because you mentioned that only one can be active at the same time.
Yes, there can be, for example, in my specific illustration, there could be 2 vector register files which can be active in a register file holder. Yes. So
Yes.
because the power supply is distributed on a register file holder level, right? So if I have more than 2 of them active within a single register file, I'll be drawing more current, and that could lead to a voltage drop across that specific register file holder. So that would affect all the cells in that network. Yeah.
Can you maybe go back to slide 28?
Which one?
28.
28. Yes.
So because I can see that these two instructions like does not depend on each other, so I don't know why it cannot be
Oh,
performed
no,
at
no,
the
no.
same
Okay,
time.
I'll clarify that. So it is not a data dependency issue actually. So the problem is because of the hardware, not because of the instructions. So the idea is if I execute both of them simultaneously, I have all 6 rows active at once, correct? So if I have all 6 rows active at once, I'll have a lot of capacitors which are switching simultaneously. So if all of them are switching simultaneously, there will be a lot of current draw and there will be a lot of heat dissipation within a constrained space, which is something I cannot have. So if that happens, then I'm exceeding the thermal and the power limitations within that area. So that is why I can schedule, that is why I'm giving you this condition which says only one operation per VRF at a time. So this is something I addressed as a weakness as well. So because of this, I am not able to execute, I mean, like I can actually run instructions on all 6 registers, but because of this thermal and power limitation, I'm restricted to only the 3 registers at a time. So with better thermal designs and with better power distribution in future, I can utilize all the registers so I can extract better compute power from the hardware. So yeah.
I have one last question about like what is the reason that this work is better than MIM-DRAM? Like what does it do different compared to MIM-DRAM?
Okay, so the fundamental idea here is there are 2 things. One is so MIM-DRAM as it is cannot handle control flow instructions is what I'm giving to understand from this paper, right? So like I can give you a simple example. So here you in PUM, so we basically operate across longer registers and we do massive parallel operations, right? So if I have to pause that to perform a single conditional check to take a decision, that would mean that would create a significant overhead, right? So that framework does not exist on conventional PUM systems. So those smaller operations are handled by the CPU and the CPU tells you how to proceed further. So that is what MIM-DRAM is doing. But over here, instead of having to go to the CPU, I'm creating a small framework on the PUM hardware itself, which will take care of all these trivial operations so that the main the main PUM hardware can take care of parallel operations on massive data units. So that is the difference between MIM-DRAM and the MPU augmented MIM-DRAM. So we are just adding the MPU unit to the existing MIM-DRAM framework to enable control flow executions on the PUM hardware itself. Yeah. So yes, that's the idea.
Thank you.
Yes. So if it's all good, I can go ahead with the discussion. Okay. So to start off with, I'll start with a simple question. So is the ensemble execution model the right approach, or do you feel there could be a better approach which a future compiler could devise for this framework? What do you feel? Your opinion. So I can give you a small prompt maybe to start off with. So you can think of an answer based on this trade-off. So it's a very straightforward trade-off. Higher level abstraction models, programmability becomes easier, but if you have more hardware aware models, you have more control over what happens in the hardware. So anyone? Okay, cool. So yeah, go ahead.
I think that it like for hardware aware models, it would not necessarily sacrifice control and efficiency, especially in case that the workload change on runtime. In those cases, then it would actually be better if it is hardware aware, so it can schedule it more dynamically. For example, if the
I didn't get you actually. Could you come again? No, I can hear you, but I'm not able to understand what you said.
Yeah. I want to point out that for hardware aware models, it would not necessarily lose control and efficiency, and sometimes it can be better for that.
No, I'm saying the same thing as well. You are not sacrificing control. You're sacrificing control and efficiency if you move to a higher level abstraction model. Sacrifice control and efficiency when compared to hardware aware models is what I'm saying. I'm not saying hardware aware models will sacrifice control and efficiency.
Yeah. Then my point is actually that you can still have the same efficiency
with higher
level abstractions if you add hardware that can handle those sort of dynamic like runtime execution decisions for you?
In fact,
So,
okay, I agree with you. And in fact, that is something that the paper talks about as well. So if you remember that the control path hardware that I explained, so that is basically doing something similar to what you just explained. So instead of having to write explicit lower level assembly instructions, I can write a high level code, and this intermediate hardware basically takes care of boiling it down and sending it to the raw hardware compute, right? So so what I am asking here is we stop at an assembler level over we stop with an assembler over there basically, right? But what if we build another compiler on top of it and not just have an assembler? So I'm talking of an even higher level of an abstraction. So I think the hardware aspect that you mentioned is something like this, I believe. So this already does that level of an abstraction, which is why you're able to go from raw assembly to you can write some high level code, put an assembler in between. So what if you write a compiler on top of this assembler, take it even like one level above? So yes. So what do you think?
like, I think it should be doable given that like we normally don't really write assembly code anyway.
Fair enough. So, but I have some issues to point out in this direction, right? So if we have to write a compiler for this, it is possible, but it is going to be extremely difficult. The reason being, if we drop the Ensemble execution model and the related hardware abstractions, we'll have to expose all the hardware details to the compiler. And most importantly, because of the third point, I have to monitor the thermal and power constraints if I don't have these hardware abstractions in the Ensemble model somehow with my compiler, right? So that is going to be extremely difficult to write. It is possible, but it is going to be very difficult. That's the idea. And as it is, I feel that if we can combine the Ensemble execution model and write a compiler on top of the same existing infrastructure, that would be better, because the MPU framework as it is closer to a hardware-aware model right now. So yes, and with this, we can actually we are already able to tightly couple the thermal power, thermal power monitoring and the data mapping constraints, and also the power related constraints with the RFH and our scheduler. So if we can build a compiler on top of the existing infrastructure, I feel that could be a more elegant solution, right? And yes, so this is a more interesting question, I feel. So now we don't have to go back to the CPU for control flow instructions. So that bottleneck has been eradicated. So control flow instructions can now happen on PUM hardware itself. But are we creating a new bottleneck? Because we are still having to communicate within different sections of the same memory, because one VRF might send data to another VRF, and this will initiate a set of a series of data transactions. So are we creating a new bottleneck on the PUM hardware itself? So what do you guys think? So I can maybe give you a setup to think about this. So MPU eliminates the CPU PUM bottleneck, but the data is still distributed across the MPUs. I mean, I have mentioned MPUs because one single entity can have multiple MPU controllers in it. So multiple MPUs. So what if there is data movement across MPUs and across VRFs? So will that be a bottleneck? If yes, why? What do you guys think? Okay. So yes, we will have a problem at a larger scale. It won't be, the bottleneck will not be as heavy as what it was for the CPU PUM interactions, but there will still be a bottleneck because with heavy communications, the on-chip communication network becomes more congested, right? So that can create a new bottleneck, and potential solutions for this could be creating a scalable network on the PUM hardware and also performing communication aware scheduling. So we already have a framework for thermal aware scheduling. We could augment that with a communication aware framework as well. So that could be another area of discussion. With that, I would like to end my presentation. So yeah, that was it from my side. Any further questions? Okay then, so thank you so much.
Yeah, then I guess that's it for today. Thank you all for staying longer. Thanks to all the presenters for really good presentations. And please don't forget to fill in the quiz, right? Thank you.